this is Dr. Amanda Fetch, also known as Dr. Amanda Analytics. As reported in the fall of 2025, two developments significantly advanced the idea of space-based data centers. The first was StarCloud-1, the satellite, which became the initial spacecraft to carry a data center class NVIDIA H100 graphics processing unit into orbit. The second was Google's announcement of Project Suncatcher, a research initiative exploring whether scalable artificial intelligence compute infrastructures could operate in space. In this video, I will explain what each effort involves, why space is being considered for future compute systems, and what the current research indicates about feasibility. Recent analysis highlights several structural limitations in Earth-based data center infrastructure. According to IEEE Spectrum, global data centers may consume as much electricity by 2030 as the entire country of Japan. Cooling requirements are also substantial. A single 1 megawatt data center can use water comparable to the daily consumption of roughly 1,000 people in a developed country. NVIDIA's October 25 article by Angie Lee notes similar constraints. Terrestrial data centers rely heavily on evaporative cooling towers and energy-intensive thermal management systems, both of which become increasingly expensive as artificial intelligence workloads scale. These pressures have led research groups and industry teams alike to examine whether Earth orbit offers meaningful advantages, such as continuous solar power, the lack of land constraints, and the ability to radiate heat directly into space without the need for water-based cooling. StarCloud-1 is described in NVIDIA's announcement by Lee as a 60-kilogram satellite equipped with an NVIDIA H100 graphics processing unit, the first time a terrestrial-grade data center class processor has been operated in orbit. IEEE Spectrum provides additional details that include the H100, includes 80 gigabytes of high bandwidth memory, and offers approximately 100 times more compute capability than any previous space-based processor. The mission is designed to support several different tasks, including processing synthetic-aperture-radar (SAR) data in real time, running Earth observation inference pipelines, executing a large language model developed by Google. Thermal management is another one of the mission's key engineering distinctions. As NVIDIA explains, the satellite uses the vacuum of space as a natural heat sink, dissipating thermal energy through radiative panels rather than water or air-based cooling systems. This significantly reduces infrastructure requirements compared to an Earth-based deployment. Both NVIDIA and IEEE outline a broader StarCloud roadmap that includes larger orbital compute platforms, multi-kilowatt systems, and eventual scaling towards multi-megawatt orbital data centers. Google, in November of 2025, their research describes Project Suncatcher as an exploratory initiative examining whether constellations of small satellites equipped with Google tensor-processing units could serve as a scalable artificial intelligence compute system in Earth orbit. Several technical areas were highlighted. One was solar power efficiency. Google notes there that in certain orbital regimens, solar panels can generate up to 8 times more power than equivalent panels on Earth. A dawn to dusk sun-synchronous orbit provides nearly continuous sunlight, which significantly reduces the need for heavy onboard batteries. Inter-satellite optical networking, Google aims to achieve communication bandwidth comparable to a terrestrial data center network. Their target involves multi-terabit optical networking between satellites spaced roughly 100 to 200 meters apart. Now, we want to note here that 100 to 200 meters is referring to the physical distance separation between the satellites. Early laboratory tests achieved 1.6 terabits per second of bidirectional communication between a single pair of optical terminals. Now, to support this, each satellite uses an optical transceiver, which is basically a device capable of both transmitting and receiving, hence the name transceiver, laser-based data signals. And so what this enables is high bandwidth exchange of information between satellites using directed light beams rather than radio frequency systems. Another area is orbital dynamics information control. So to maintain tightly clustered formations, Google modeled satellite motion using Hill-Clohessy-Wiltshire equations, which is basically a standard analytical method for describing relative orbital motion, and refined these models numerically using the JAX, so that's JAX, machine learning library. Their analysis suggests that at an altitude of approximately 650 kilometers, only modest station-keeping propulsion would be required to preserve stable formations with 100 to 200 meter spacing. Then radiation tolerance of Google's Trillium tensor processing units. Google tested its Trillium version 6e tensor processing unit under a 67 mega electron volt proton beam. And so the results showed no hard failures up to 15 kilorads silicone equivalent, which is nearly 3 times the expected 5-year mission dose of 750 rads for a shielded spacecraft. High bandwidth memory was found to be the most sensitive component, though remaining within tolerances for projected missions. Another area was the economic feasibility. So Google's analysis suggests that if launch costs fall below 200 United States dollars per kilogram, that cost level may be achievable in the 2030s. If this is the case, orbital compute systems could begin to approach cost parity with terrestrial data centers on a per kilowatt basis. As a next step, Google and Planet Labs plan to launch 2 prototype satellites in 2027 to validate these models. Although both efforts address the concept of space-based compute, they emphasize different timelines and technical approaches. NVIDIA and StarCloud are demonstrating near-term feasibility by flying a functioning H100 graphics processing unit and evaluating practical workloads such as SAR processing and large language model execution. Google is examining long-term architectural considerations and including tightly spaced satellite constellations, multi-terabit optical networking, and radiation-tolerant tensor processing unit hardware. Both groups identify similar motivations: the limitations of terrestrial power and cooling systems, and the potential physical advantages provided by the space environment. Each source identifies several engineering challenges. On the Google side, maintaining satellite spacing of 100 to 200 meters is one, ensuring reliability of multi-terabit optical communication links, also improving radiation tolerance and hardware longevity for tensor processing units. In addition, developing systems capable of multi-year reliability without direct physical servicing. Now, if we look at the NVIDIA and IEEE spectrum side of the equation, they're looking at ensuring multi-year performance of graphics processing units in radiation environments, scaling from a 60 kilogram demonstrator to multi-kilowatt or larger orbital systems, managing thermal loads at higher power levels, establishing viable economic models for long-term orbital compute operations. And so in closing, these findings show that while early demonstrations seem to be promising, there's still significant engineering work that needs to be done. And so in the end, no matter which approach becomes dominant, the near-term demonstrations led by NVIDIA and StarCloud, or the longer-term architectural research pursued by Google this year in 2025, marks a measurable shift. And so both efforts indicate that space-based compute is evolving from this theoretical idea into an active field of research and engineering. The next several years will really determine how viable these systems are and whether they can complement or eventually augment Earth-based data center infrastructure. So to continue this discussion, I have a question that I'm going to also pose in the comments. In your opinion, which approach do you think is more likely to influence the future of space-based compute? Do you think it's NVIDIA's near-term hardware demonstrations? Or do you think it's Google's long-term constellation architecture? Welcome all perspectives from across the AI, aerospace, space, and engineering communities. Thank you.